Welcome to the third lecture of Physics 401A. In this lecture, we learn the method of calculus of variations. The principal objective of this method is to find the curve for which some line integral has a stationary or extremum value. This method is extremely useful for us because next week, just by using this method, I will derive the governing equation for Lagrangian mechanics. Let's now pose the problem from a general point of view. Okay. Let's take a mathematical function f, which is a function of y, y dot and x, and it is defined on a path y between two fixed x values, x1 and x2. Y dot is nothing but dy dx, which is the slope of the curve y of x in the yx plot. Now, as we can easily understand that f has an explicit dependence on x, but f also has implicit dependence on x through y and y dot. Now, what is the real meaning of this sentence which is skipped over here? That for simplicity we start with one-dimensional problem. Now, to understand this, we have to go to the physical example of this type of problem, where we can think x is like equivalent to time t and y is the positional coordinates and y dot is the corresponding velocity coordinates. Now, if we only have one-dimensional problem, then we will only have one position coordinate and corresponding one velocity coordinate. So this is the meaning of one-dimensional problem. If we have multi-dimensional problem, then we will have y1, y1 dot, y2, y2 dot like this. Okay. Now we construct a particular line integral which is given by j, and it is the integral between x1 to x2 f of dx. Right? Now, if you explicitly write y and y dot in terms of x and then finally integrate that with respect to x, then finally you will be given just a number for j, right, or a value. Now, our objective is to search for the kind of function or search for that particular function y of x, so that the value of j, hence calculated, has a stationary value. And stationary with respect to which? Stationary relative to the paths differing by an infinitesimal amount from y is equal to y of x. Right? So y is equal to y of x is nothing but a path here for our problem. This is a path joining these 2 points x1 and x2, and if you just change y to some y1 or y star, whatever, you will have another path. Here you can see that the red solid line gives you y of x, and the red dotted lines are giving you two other functions, right? Let's say y1, y2, whatever. Okay. Now we have to understand that this red solid line is that function of x which gives us the stationary value of j. Stationary can be maximum or minimum. Okay, any extremum value. And another way of saying this mathematically is that the variation of j must be vanishing with respect to its neighboring paths. What is the meaning of neighboring path? That means the paths which are situated infinitesimally apart from the correct one. So although this picture doesn't show really the infinitesimal distances from the solid one, but we have to understand that those dotted lines are very, very close to this solid line. Okay. How to write that mathematically? So we can write such arbitrary curves, such arbitrary neighbor curves of y is equal to y of x as y of x and alpha, where alpha is taken as a second variable by varying which for a given value of x you can have a different value of y, right? That's exactly you can understand from here that for a given value of x if you just vary y to y plus delta y, right, you can have the value which is on the another curve. Okay, and you can simply write that departure as alpha times eta x. Alpha because this is the smallest parameter, this simply shows that the distance or departure is very small, and eta because eta of x because this distance is also a function of x. For different values of x, you can see different amount of departures. Okay, so this is the function. This is the function which we already suppose that is giving the stationary value of j, and this is its departure. Now this function eta x should also satisfy two conditions. One is it should vanish at both x1 and x2, because whatever be the departures at the starting point and the end point, they should be identical to the original function y. Okay, because we don't change the initial and the final point. Between that, we can change the paths. Okay. The second one is, of course, eta x should be well-behaved function. That means it should not contain any singularity or continua or discontinuity. Okay, and then also it should have continuous first and second order derivatives in the same interval between x1 and x2. Okay. Now we can easily understand, finally we are given with a family of parametric curves. So these curves which are parametrized by alpha, that means you can change, you can travel from one curve to another, actually you can navigate, okay, by changing the parameter alpha. Or you can say that, okay, now my function y is not only a function of x, I now have two independent variables, x and alpha. That's another way of saying, okay. Then if you write for that arbitrary general function, which includes the real function as well as all the neighbor function. Real function means the function which we are trying to find, for which j has a stationary value. Okay. Then for this generalized family of curves, you have another j. So it is no longer now just a pure value, but it is now a function of alpha, because this is only integrated over x. So alpha is over there, so it is j of alpha. Okay. Now for j alpha should be stationary, that is minimum or maximum locally at least, dj d alpha at alpha is equal to 0 should vanish. Why at alpha is equal to 0? Because by construction we have assumed that at alpha is equal to 0, the curve is giving the the real curve. Okay, the curve with stationary value of j integral, right? Now if we use Leibniz rule of differentiation under an integration, the dd alpha basically enters into this integration as del alpha. Okay, because alpha and x, they are mutually independent. Okay, the dd alpha just enters like a partial differentiation with respect to alpha. So finally you can say that the condition for stationary j is nothing but dd alpha of integration f dx is equal to 0, which is equivalent to integration del f del alpha dx will be equal to 0. Now if you just expand then del f del alpha, okay, you can easily write that is exactly equal to del f del y del alpha plus del f del y dot del alpha, plus there will be a term del f del x times del x del alpha. Now as x and alpha, they cannot see each other, this term would vanish. Okay. Okay. Now let us consider the second term of this equation, that is this one. Okay. If we notice this term, then we will see del alpha y dot is equal to del alpha of dy dx. Now y is a function of x and alpha, and there is no implicit dependence of x and alpha. They are completely independent. They don't know each other. Okay, that's why in such cases dy dx is equal to del y del x, and the same thing for alpha. Dy d alpha will be equal to del y del alpha. You can do that from the, starting from the first principle of calculus, you can do that and you can check it. Okay, then you can simply write del alpha dy dx as del alpha del y del x. Then you can interchange the partial differentiations within themselves. Okay, and you will have that equal to integration from x1 to x2 del f del y dot del 2y del x del alpha dx. Now again, you can easily understand that again I can write this del x as ddx, right? That step I have just skipped, so you can again write that del x as ddx, and or you can just simply say that from this one you can interchange the partial and the total derivatives. Okay, and you can finally write here del f del y dot ddx del y del alpha times dx. That's also correct. Okay, then we can do integration by parts. Okay, now that will just give us this first term unchanged and this term, so ddx del y del alpha dx integrated over x2, integrated from x1 to x2, and which is simply del y del alpha within x1 and x2. And if we now remember what del y del alpha is, from definition we can simply say that del y del alpha is nothing but the function eta of x, right? We simply substitute that and we will see that eta x from our condition should vanish at x1 and x2, so this term will vanish. Then the next term will come as minus integration from x1 to x2 ddx of del f del y dot, again del y del alpha dx, right? You can do that and check. Now combining 1 and 2, so that was 1, okay, and that was 2. We can finally write the condition for that the curve y x comma 0 be the path of stationary action, and that is simply integration from x1 to x2 del f del y del alpha minus the second term as we have calculated in 2, okay, as ddx of del f del y dot times del y del alpha, and the whole part is multiplied with dx, okay, and the whole integration is evaluated at alpha is equal to 0, and this is equal to 0. Now if we just try to understand what the meaning of this f in general, they are the generalized f including all the real curve or real path and all possible neighboring like infinitesimally departed curves from the real one. So they are in general designated by f of x and alpha. When I say explicitly alpha is equal to 0, we have to replace this condition over here, okay, and we have to see what happens. Now you can see that this del f del y minus ddx of del f del y dot we can take separately, and the whole thing will be then multiplied with del y del alpha, that is the common factor, times dx, okay. Then you can easily say that finally I am writing the total expression into two parts. So this will be finally the integration from x1 to x2 del y f of y x0 y dot x0 and x. So here basically we have already started to evaluate the whole thing for alpha is equal to 0, right? So that simply gives us the real curve itself. Okay, and the same thing for here. So from all possible curves, here we are just extracting the real curve. Okay, and then we have this factor which is del y del alpha, and that also should be evaluated at alpha is equal to 0 times dx is equal to 0. Sorry, the 0 is not very much visible over here. So I now call this f of y x0 and y dot x0 and x as the f real, because this is the real path which gives us j to be stationary, right? And for that we have this condition. So this is the condition we finally have for f real. Okay, again we can say that del y del alpha at alpha is equal to 0 is eta x. So this is nothing but eta x times dx times the whole factor, that is del f real del y minus ddx of del f real by del y dot is equal to dot total thing integrated from x1 to x2 is equal to 0. Now this is 0 for arbitrary choice of del y del alpha, that means eta x. We can actually choose eta x arbitrarily. Okay, always picking the condition, keeping the conditions that eta x should vanish at x1 and x2, and they should be smooth with having like first and second derivatives continuous. Okay, we can actually choose any function. Okay, and dx is also arbitrary. So if they are arbitrary, the only condition, the only possibility that the integration always vanishes is that this integral within this bracket should vanish. And this is the condition for f real to give stationary value of j. Okay. Now let us have a look at this quantity. Del y del alpha, alpha at alpha is equal to 0 times d alpha. This is nothing but the variation of y keeping the value of x unchanged, right? That is known as the variation of y. Okay, the variation means not any variation in our context. The variation means that we just change the parameter alpha and we keep the x or the intrinsic independent variable, okay, unchanged. So if x is equal to time, which is the most of the case for classical mechanics, okay, this means that this is a variation where time is unchanged or time is frozen. So this type of variation is also known as virtual variation or virtual displacement. Okay, so delta has a specific meaning. Okay, now delta y is the distance between the real and its neighboring path for a given x, as I just said. So that you can now think of the figure which I have drawn here. So this is the delta y, this as it is written. Okay. Now you can say that using the same type of concept, okay, we can also say the infinitesimal variation of j alpha about the correct path is given by del j del alpha dot d alpha. So that is then can be called as delta of j. So this is the variation of j, or in classical mechanics context you can also say the virtual variation or virtual displacement of j. That is also possible. So an equivalent way of saying j is stationary is the virtual displacement or the variation of j is also vanishing. So whenever we say in the context of this calculus of variation or classical mechanics using this calculus of variation, that something's variation or variation of some quantity is 0, that simply means its change or the change of its value, always keeping the value of the intrinsic independent variable unchanged. That is the meaning of that. Now, if you try to understand carefully the whole procedure which is followed over here, you will understand there are four type of variables and functions. Okay, so one is x. This is the intrinsic independent variable of the whole problem. Then y and y dot, both of them are functions of x only. Then comes f, which is a function of y dot and x. Then finally j. As j is nothing but the integration of f over x, then j should be independent of x and j is a function of y and y dot only. Now the whole methodology is nothing but to find a function y of x for which another function of y, which is f, of course y dot is there, but once you know y, you can y of x, you can easily calculate y dot of y dot of x. That's true. Okay, so the thing is that to find out the proper y of x, so that j or the integration of f dx has a stationary value. Okay, so j is nothing but a function of functions. If we talk about directly j and the intrinsic independent variable x. So y is a function of x and j is a function of function. J is a function of y, so it's a function of x. Okay, so this type of thing is known as the functional of in mathematics. Okay, so here the total problem reduces to find the appropriate function for which the corresponding functional, which is j, is stationary or has a extremum value, let's say minimum or maximum, whatever. Okay, so that is that. That's the thing. So yeah, next week we will understand for physical systems what is these functions and what are those corresponding functionals. Okay, so people who are not familiar with functions and functionals, for function you know that you give a value of a variable and you have a value out of that function. For functional you give a function as input and you have a value out of that functional. Okay, now after all this discussion, let me ask you this question that was done for 1D problem, that means only one pair of y and y dot. What will happen if f is a function of y1, y2 up to y small n and y1 dot, y2 dot up to y n, y dot small n and x. So that means an n-dimensional problem. What will be that? Think and tell me. Okay, thank you very much.